Welcome to the Explainer. Today, we're totally cracking the code on how abstract coordinate geometry actually translates into real-world physical distances. You know how your mapping app just automatically knows exactly how far away your destination is? Well, it all starts with the foundational mathematical concepts we're going to unpack right now. All right, let's dive straight into a practical setup here. We're looking at a map showing the relative locations of a couple of villages, Rohan and Sohan, along with major highways like the Delhi-Agra route, and some intersecting local roads. Now, this isn't just a random drawing, right? It's literally a classic real-world geometry problem just waiting to be solved. We've got an intersection point, distances along those highways, and a local road cutting right across the middle. Which naturally brings us to our central question. If we want to find the exact length of that local road right there, the one labeled AB, how exactly do we do that? When you've only got relative positions or grid coordinates, you can't exactly just slap a giant physical ruler on the ground. We need a specific mathematical tool to bridge the gap between points on a grid and actual physical distance, a tool that we don't quite have just yet. Section 1. Deriving the distance formula. So to solve our math mystery, let's take a quick step back and look at the origin story of the secret weapon we need. What's really fascinating here is how it takes something you already know inside and out, Pythagoras' theorem, and just overlays it right onto a Cartesian coordinate grid. Check out the right-angle triangle formed by points A, B, and C. The distance we want to find is the hypotenuse, line AB. But instead of just handing us the lengths of the sides, the grid gives us coordinates. We've got x1, y1 for point A, and x2, y2 for point B. And here's where the magic happens. Think about the base of that triangle. It's really just the difference between our x-coordinates. And the height? Just the difference between the y-coordinates. From there, it's pure Pythagoras. You just square those differences, add them up, and take the square root. Bam! Physical distance. It turns out the distance between any 2 points is simply the square root of the sum of the square differences of their coordinates. Section 2. The training ground basic applications. Okay, so now that we actually have our formula, let's test it out. And you'll notice how it beautifully simplifies if one of your points happens to be the origin, 0, 0. Because subtracting 0 changes absolutely nothing, right? So the formula for the distance from the origin just collapses down to the square root of x squared plus y squared. It's such a fantastic shortcut when you're measuring directly from the center of your map. Let's actually see this in action. Say point A is at 3, 6 and point B is at 0, 2. We just plug those right in. The math here is incredibly clean. 3 squared is 9, 4 squared is 16, add those up, you get 25, and boom, the square root gives us an exact perfect distance of 5 units. It works beautifully every single time. And here's a pro tip. This formula is totally a two-way street. If you already know the final distance, but you're missing one of the specific coordinates, you aren't stuck at all. You just plug in that known distance, square both sides of the equation to wipe out that square root sign, and solve the resulting quadratic equation using basic algebra. It's literally just working the whole logic in reverse. Section 3. The boss level, the circumcenter. All right, let's level up to a much more complex application. One that's going to require us to use our formula multiple times simultaneously, finding the circumcenter of a triangle. Now, quick definition here. The circumcenter is that highly specific point perfectly balanced in the middle of a triangle that is completely equidistant from all 3 of its vertices. Basically, if you drew a circle using this point as the exact center, the circle's edge would perfectly kiss all 3 corners of the triangle. It's a total geometric sweet spot. And this brilliantly illustrates exactly what we're going for. We've got triangle ABC with our circumcenter point P right there in the middle. We're looking for the exact coordinates of P, which we can just call x and y. The visual makes the math requirement super clear, doesn't it? The distance from P to A absolutely must equal the distance from P to B, which also has to equal the distance from P to C. So, to actually solve this, we just set up our distance formulas to match each other. Distance PA squared equals PB squared, and so on. When we expand out the algebra and start canceling out the squared terms, which, by the way, is just incredibly satisfying to do on paper, we can finally solve for our exact center point. And doing that math reveals that our circumcenter sits perfectly at the coordinates 3, 3. Section 4. Resolution. Solving the map mystery. Well, we've mastered the basics and conquered the boss level, so let's head back to our initial map to finally crack this case. Looking back at our village setup, remember we were asked to find the coordinates of points A and B and then figure out the exact length of that local road connecting them? Notice how the map is naturally set up on a grid? Yeah, that's our Cartesian plane just hiding in plain sight. The scenario lays it out perfectly for us. The two main highways intersect, creating an origin point right at 0, 0. We're told that point A is 10 kilometers away along one highway, so let's just call that the x-axis. That means point A sits at 10, 0. Point B is 12 kilometers away along the other highway, the y-axis. So point B is at 0, 12. Look at that. We've successfully translated physical geography into exact workable coordinates. And now for the grand finale. To find the actual length of that local road AB, we just use our simplified distance from the origin formula. We square that distance of 10 to get 100. We square the distance of 12 to get 144, add them together, and we find that the shortest absolute distance for local road AB is the square root of 244 kilometers. Mystery mathematically solved. But before we wrap, let me leave you with a little something to ponder. Today, we use this formula to calculate exact distances on a two-dimensional perfectly flat map. But, as we all know, the Earth definitely isn't flat. So, think about that crazy leap from flat coordinate grids to curved three-dimensional space. How do you think your phone's GPS routes you across a 3D globe? The math certainly gets more complex, incorporating z-axes and spherical trigonometry, but the core foundational logic? It's exactly what we just did here today. Mastering these coordinates is truly just the very beginning of your journey into real-world navigation. Thanks for joining me on this explainer, and keep questioning the math behind the map.